Next, we'd like to discuss the science of hurricanes, and we're going to do that with Professor Ricky Rude from Climate and Space Sciences and Engineering at the University of Michigan. Ricky is an expert in hurricane science, and I've got some hard questions for him. Ricky, first of all, 2017, what the heck? Why so many hurricanes this particular year? Is there something unusual?
Well, the hurricanes vary in the Atlantic from year to year, and it's dependent upon some special conditions. One of them is warm seawater. One of them is that there's not much variation in the wind as you go up in the atmosphere, because that keeps the hurricanes from forming. And then it's also helpful to have these disturbances coming off of Africa, off the Sahara Desert, that help organize them. So we see years sometimes with more hurricanes and sometimes with less. One of the things that is extraordinary about this year is that these three things have aligned, and the Atlantic and the Gulf of Mexico and the Caribbean are extraordinarily warm.
Now, often when we have more hurricanes like this, it's also there's an influence of El Nino or La Nina. How does that play a role this year?
I think currently we're at more of a neutral stage of El Nino and La Nina. We had a strong El Nino, and when there's an El Nino, we tend to have fewer hurricanes in the Atlantic. When there's a La Nina, the wind shear, that change of the wind with altitude, is usually weaker, and we might have more. But I believe with regard to the tropical situation, we could not be said right now to have an extraordinarily strong El Nino or La Nina.
The triggers for many of these storms are easterly waves coming off the coast of Africa. Has there been any increase or change in these easterly waves this year?
To my knowledge, there hasn't been what you might call a secular change. We see more of those waves in some years than the other, and we are seeing waves, those easterly waves, coming off of Africa, coming off the Sahara Desert, which occurs because of the very strong temperature gradient in the Sahara, sets up this very particular type of wave that propagates to the east. We don't often see waves propagating to the east in general, so they're a particularly interesting phenomenon. But to my knowledge, we are seeing a year that has a number of them, but we're not really seeing what you might call a climate trend in easterly waves.
Now, when we track these storms, it's not uncommon that the storms will perturb the ocean. They mix the water to a depth and leave a trail of cooler water behind. But as I understand it, we've had Irma, and then there's Jose, and Jose more or less followed Irma and didn't really seem to decay. Is there some change in the mixing that we're seeing in these storms?
I'm not sure that we would be seeing a change, particularly in the mixing that's associated with the interaction of the air and the ocean. But I think one of the things that is extraordinary this year, and one of the things that's definitely associated with climate, is that with climate change, is that we are seeing the sea surface temperatures increase. And more than that, we're seeing the ocean heat content. So the amount of heat that's stored in the upper levels of the ocean is increasing just one year after the other at this point. That's where most of the heat of global warming goes, is to increasing the ocean heat content. So it's possible that the mixing is actually churning up water that's not as cold historically, which would have an impact on the trailing hurricane.
The forecasting for Irma, although it changed location sort of towards the end and went up the west coast of Florida, for the most part, it was pretty good forecasting, best I could tell. The models varied. I'd like you to speak about the variation in various forecasting models for hurricanes.
So when we use models to provide guidance for hurricanes, We rely on sort of two classes of models. One of them would be the global model, and by global, we mean that it attempts to, or doesn't attempt, its domain is the entire globe. And then we also rely on regional models, which allow us to focus on only the hurricane region. At the early phases, what we really do rely on most are the global models. And in this case, the global models were providing reasonably good guidance, well more than a week out. Um, this is characteristic, perhaps, of these types of hurricanes. They're, I think, called Cape Verde hurricanes, that are often associated with those African easterly waves, that they get picked up relatively early, and the models can provide us a longer lead time on some of those than, say, on Harvey, which really formed right off the Texas coast. So there are different characteristics there. Um, I think all in all, the models did an extraordinary job of providing guidance that there was high likelihood of a hurricane hitting Florida sometime in advance. There will be some argument about the quality of the different models, the different global models. That's already in the press floating around. That's a long-standing issue about the differences between the European Centre's model and the National Weather Service's model and the UK Met Office model. So that'll be an issue. But hurricanes and their tracks are relatively difficult to predict more than a few days in advance. And what you saw as it got closer and closer to Florida, that as we got more and more data, as the atmospheric state at a particular time became well defined, the models started to, say, alter that track in terms of the details of where it would hit on land. These, from a global perspective, were not big alterations, but for a narrow state like Florida with a large hurricane like this, these shifts of a few tens to perhaps hundreds of kilometers, a small number of hundreds of kilometers, have very important consequences on the impacts and how you plan and how you prepare your evacuations.
Let's follow up on that issue of the modeling. You mentioned the data that goes into these models is key to the quality of the models. What is the data that goes into these models now?
So the way weather forecasts are done, we use observations to essentially take a snapshot of what the atmosphere and the ocean and the land surface look like at a particular time. And then what we do is we propagate the disturbances or the weather that is present at that particular time. We propagate that forward for the weather forecast. So the data which go into those models is, and the treatment of that data is probably the single most important scientific uh, decisions that are made in terms of the ability to do a forecast, though there are many important decisions that all need to be made in concert. So that data comes from many sources. It comes from balloons and it comes from surface stations. It comes from airplanes. And increasingly, and by far the largest quantity of data, comes from a set of environmental satellites. And of particular importance in weather forecasting is the data, or are the data that come from the polar orbiting satellites, which provide us information about the vertical structure of temperature and the vertical structure of moisture in the atmosphere. So it's a combination of data from many sources, and there are literally millions, if not billions, of observations incorporated into each weather forecast.
Can you describe the value of this new satellite, GO 16? I mean, the imagery from it is phenomenal. So, is that going to help us with forecasts in the future?
With regard to the science of using geostationary data like that, it clearly provides a lot of information about sort of the position of the hurricane, the structure of the hurricane, the rain bands, and it helps a whole lot on sort of the short term forecasting. Those data have proven difficult to incorporate into the global forecast models, though we've made some progress. The reason it's difficult to incorporate them into the global forecast models is that they are staring down, and generally you see a very thick slab of the atmosphere. So you do not see a lot of vertical structure. And the vertical structure and how the temperature varies with height, how the moisture varies with height, is crucial to a good forecast. There's that train.
Coming through. Good. I'll let the train pass for a second. All right. The real elephant in the room here is that the temperatures of the oceans are warming. You said a moment ago to greater depth, probably. As we know that the amount of moisture the atmosphere can hold goes up exponentially with temperature. Given those two, that and the understanding that the energy of a hurricane comes from the condensation of water, is logical to expect then that the intensity or duration of hurricanes might increase in the future. What's your expectation?
So this is a problem that there's a lot of research on what's happening. One of the ways I think about this problem is, as you just stated, the energy available through the warm water and through the warming ocean has got to be having some sort of impact on these storms. I don't see how you can add energy to a system and not expect it to have some sort of impact. The question, is how is it changing these storms, and are they different in some measurable way than historically? The people who do the hard research on this, honestly, they end up with arguments about whether or not, the frequency and the intensity of the storms will change or if they have changed. Most of the literature that I've read so far says that it is reasonable to expect a larger number of these very strong storms. But I think what is perhaps most interesting and what is perhaps ultimately going to be most important, if you look at a storm like Irma and compare it, say, to Andrew, um, the intensity of Andrew, the wind speed when it hit land was extraordinary. But if you look at the size of these storms, the size of these storms that we've seen in the last few years is enormous compared to storms, even 1 and 2 decades ago. And what is interesting to think about that in terms of energy is that the amount of energy that's actually existing in these storms, though the peak wind might not be quite as large, the amount of energy that is accumulated and is swirling around in these storms is much, much larger. And given the amount of energy in the spatial scale, and particularly when you get a slow moving storm, the potential devastation, especially perhaps from flooding, is the potential of that being greater. I think is very high.
And of course, the power of the wind goes up as the cube of the wind speed. So even small changes in wind speed and area are going to have a big impact on the total energy and power of a hurricane.
Absolutely, and then the size and the wind interacting with the ocean, pushes up the water that is associated with these storm surges. So you get an interesting phenomenon like we just had in Florida, where some time after the storm had reached its peak, a city like Jacksonville, Florida, is getting extraordinary flooding, and with an extraordinary combination of rain and storm surge and perhaps increasing sea level.
Well, Ricky, thanks so much for your insights into these questions, and we look forward to hearing more about your research in the future.
You're welcome, and thank you for asking.